Channel Chemistry, the mystery of molecules. So today we shall discuss a very interesting as well as important topic, that is resonance energy of different aromatic hydrocarbon and their chemical reactivity. Okay, so lots of interesting thing to be learned in this video. Please watch this video until the end. And secondly, I have already discussed many details lecture on such topics previously, so this video will be point to the point, short and specific. So if you want further details, please visit those corresponding videos, but you can consider this video as a summary. So let's start. If you look at the molecule, the famous aromatic molecule, that is benzene. So this, if you look at its resonance energy is 36 kilocalorie per mole, whereas its next higher analog, that is naphthalene, whose this resonance energy is 61. Now if you look at this, benzene has this molecule has one benzene nucleus, 6-member ring, but this naphthalene you may consider it's a 2 benzene nucleus fused together. For better understanding, means which one is more stable based on aromaticity, you need to think that one benzene have 36 kilocalorie stabilization, 2 benzene 61 by 2 equal to 30.5 kilocalorie per mole. Okay, so from this thing you can understand who is relatively more stable. Obviously benzene. And if you look at this anthracene, it is 84 by 3, so per benzene nucleus wise you can say it's 28. So I always suggest student, please don't get confused that sir, here in case of benzene it is 36 kilocalorie per mole, whereas in case of toluene 61, in case of anthracene 84, and in case of phenanthrene 92. So who is maximum stable with respect to per nucleus? Benzene is maximum stable. Second thing, we know the stability means it's inert for chemical reaction. It's relatively inert to undergo chemical reaction. So if you look at the trend in chemical reaction, benzene among these four, means benzene, this naphthalene, anthracene and phenanthrene. So among these four, benzene is least chemically reactive compared to them. What type of chemical reactivity? You may consider that is oxidation. Okay, if you want to oxidize benzene, you need a very drastic condition, whereas you can oxidize naphthalene easily, and obviously in this case one nucleus will be oxidized preferentially. After that, if you want to do the second oxidation, you need to give a very harsh condition. See, in case of anthracene, now question may come, which benzene nucleus will undergo, because in this case there are 3. So actually during the reaction, this middle benzene nucleus undergo oxidation, and you can say that 9, 10 anthraquinol, so dihydroxy anthracene, you may consider those kind of thing. Why such kind of thing happens? Because during the oxidation process, in this way 2 benzene nucleus are saved, means this and this. So one benzene nucleus means 36 kilocalorie per mole. In this case, what is this? It is 36 into 2, that is 72 kilocalorie per mole overall safe. Now if you think, if the terminal one, what do I mean, this terminal one of anthracene undergo oxidation, then what is the resonance energy saved? That is 61. So in the middle one you will have resonance energy 72, in the terminal one 61. So in this case, which one is stable? Obviously the oxidation of the middle one resulted in relatively lesser stabilization of the product. That's why the oxidation of anthracene always happens in this 9. So this is the 9 and this is the 10. So this 9, 10 position. Whereas if you look at phenanthrene, some different kind of activity observed. In this case, where the oxidation occurs, this double bond. So if this double bond oxidation occurs, see, look at very carefully that these two, these and these 36 are safe. So that's the advantage. That's why you always see that these this double bond of anthracene are very reactive compared to other double bond in this molecule. Okay, so this is the indication how aromaticity controls the reactivity of this polycyclic aromatic compound. Okay, now, so, and the second thing, as I told you, for better understanding, you may calculate the Re with respect to number of benzene nucleus present. Now a question, see, in styrene, which have a benzene nucleus attached to a double bond. So which double bond is expected to react earlier, and which double bond means, what do I mean, this double bond 1, that is external double bond, or double bond inside the benzene ring? Which double bond? Obviously this this double bond, because in this case loss of resonance energy means reaction of this double, after the reaction of this double bond, the loss of means styrene external double bond, so the loss of Re is minimum, whereas if you react the double with this benzene, the loss of Re is far more higher. So that's why, so because of this point or this logic, the reactivity of styrene you can see on this double bond part. Okay, now so based on that I am giving one this MCQ, oxidation of this is actually quinoline. So what is the product? 4 options are given, so at one hints also given. I expect that you will pause and try this question. I shall give the answer at the end. So now let's continue our discussion. So not only 6 member, benzene is a 6 member. If we look at the 5 member heterocyclic compound, what is the pattern? If you see the resonance energy of this cyclopentadiene, this is 3. You will say, sir, 3, why? Because see, this carbon is not sp2, it is not sp2, this is actually sp3, and that's why it is not actually aromatic, because this is a CH2 group. So cyclopentadiene is not aromatic. Remember students, cyclopentadienyl anion is aromatic. Okay, so that is the thing. Now if you look at furan, this furan, pyrrole and thiophene, what is the difference? See, furan has Re of 16 kilocalorie per mole, okay, whereas this pyrrole 22 and this thiophene is 29. Now why? See, this in this case furan, the electronegativity of oxygen prefers to keep the electron density on itself, and what is the concept of aromaticity? Completely delocalization. Oxygen prefers to localize electron density closer to itself due to its electronegativity, but the aromaticity concept is completely against of this. So these two cancels each other, consequently the aromatic stabilization of this furan only 16 kilocalorie per mole compared to this pyrrole, which is relatively higher because electronegative nitrogen is slightly less than oxygen and sulfur is more or less compared to that. So second thing, now what is the consequence of this chemical reactivity? You can see this furan act as diene very efficiently. I have already discussed this thing previously, this 5 member heterocyclic as diene. So furan can react very efficiently as a diene, whereas thiophene and pyrrole, they are not that much interested. Okay, so furan malic anhydride, there's a very fast reaction thing. So why furan reacts very efficiently? Because since its aromatic stabilization is less, means it is more reactive. If it is more reactive, it will react efficiently for Diels-Alder reaction. Okay, now another interesting point is this indole nucleus. Here the Re is 49 means there are already 36 included. So if you remove this 36, what is left? That is a 13 kilocalorie per mole. Why this? See, in this case one double bond is in common with the benzene nucleus, so consequently, so that is not completely involved in the delocalization of this indole, means this delocalization of this 5 member ring. So consequently what happened? So it is not that much delocalized. Second thing, if you look at the aromatic electrophilic substitution of these 3 5 member heterocyclic compound, their selectivity is mainly C2. Okay, because after aromatic electrophilic substitution, the cation, you may consider this X, this is E, this. So this is further resonance stabilized by this second double bond, whereas if you look at this indole, in this case 7 double bond means this benzene nucleus, so its aromatic stability of that benzene will be hampered. Consequently, indole gives selective reactivity on this C3 position. So that's how the aromaticity controls the chemical reactivity as well as selectivity. Second thing, indole is far more reactive compared to pyrrole. Why? Because in this case, during the aromatic electrophilic substitution, this sigma complex form, and this formation of sigma complex is associated with this loss of aromatic stabilization. But you think if the compound itself is less stable, then it's more reactive. The same example just few times before I have given for furan, why furan is very reactive for Diels-Alder reaction compared to pyrrole and thiophene, similar way. Okay, so this is about the 5 member ring. Now let's discuss about the 6 member ring. See, as I told, benzene have Re 36 kilocalorie per mole, whereas pyridine is 28. Why? Similar reason like furan, because nitrogen is more electronegative, so it prefers to localize the electron cloud closer to itself due to its electronegativity, and the concept of aromaticity is completely against, means aromaticity means complete delocalization. So those two are against each other, so extent of stabilization is relatively less for pyridine. And if you look at quinoline versus isoquinoline, just look at this example little carefully. Quinoline has 47 kilocalorie per mole, whereas these isoquinoline have Re less than quinoline. I didn't get exact data, so if you student know, please mention in the comment box. Now, so why this? If you look at the resonance structure, means this, what this double bond it can withdraw, so positive charge will come here. So I am not focusing on the other, because the other benzene nucleus is common for both of them. Okay, so this, now there is one double bond. What can happen? This can undergo another canonical form. How it can come? So what it will do? Positive charge will come in the para position, so it will come here, the negative charge on nitrogen. So this thing. So now you can see in this case two canonical form possible, but if you look at this isoquinoline derivative, only one canonical form possible. How? So this. So this is the nitrogen. So what happens? It can withdraw the electron density from here, so positive charge will come here. See, the other pi bond here, it can't directly help to stabilize this. If it want to do it, you need to hamper this benzene nucleus, which we don't want to do, because we are comparing, and since in this case two benzene nucleus are common, so we are comparing. Why? Less resonance energy of isoquinoline is less than quinoline. From this canonical form you can explain. Okay, fine. So okay, got it. Now let's come to another interesting property, that is keto and autotunism. We know that phenol prefers to remain 100% enol form. Resource enol have some amount of keto, some amount of enol, it's in equilibrium. But whereas fluoroglycinol prefers to remain in its keto form. Okay, why? Because we know that this C double bond O is more stable energetically compared to C double bond C. So consequently, if you take an aliphatic keto compound, for example this one, this keto will prefer to remain in keto form because the keto is more stable. But in this case aromaticity is the driving force, that's why majority was 100%. Now in this case of resorcinol, so this is actually resorcinol, now there is a competition between whom? Aromaticity versus keto form stabilization. So some amount keto, some amount aromaticity, but in this case for fluoroglycinol, the stabilization due to the 3 keto form overcomes the aromatic stabilization, that's why it prefers to remain in this tri-keto formation. Okay, now so from this understanding we can conclude and make some extension. But if you look at benzene, it's a 6 pi electron. If you look at biphenyl, it's 12 pi electron. If you look at this anthracene, it's actually 14 pi electron. And if you look at this triphenyl, it means 3 benzene nucleus separately attached together, it is a 18 pi electron. All are actually aromatic. So not only that, if you go from here to macrocycles like this porphyrin, it's 18 pi electron, we know all are actually electron rich. Now why I have given this? See, from if you increase the conjugation or if you increase the number of pi electrons involved in the aromatic stabilization, you are actually creating an electron reservoir. What do I mean by this? So you can think that you have a water reservoir or pool. From the pool you can take one bucket of water, or if you take one bucket of water, the amount of water in the pool will not change significantly, or if you add one bucket of water, the water amount will not change significantly because the pool have enough water. Similarly, you think electron. So what happens if you increase the number of pi electrons and they are in conjugation, and if they are stable because of aromaticity, so what they can do? They can give electron, they can take electron. Now you will say that, sir, if you say that they give or they take, then their aromaticity will be hampered. Why do they will do? Actually, when the number of electrons are more, so that in that case the minimum effect happens when we add external an excess electron and if we withdraw an excess electron. So you may consider it's a reservoir place. You can keep something on this or you can take, but effect will not be that much. But in this case, if you compare, if you add 1 electron on benzene or if you withdraw 1 electron on benzene, the consequence will be higher. That's why the process is very difficult. And if you go one step further from this small macrocycle to big macrocycle like graphene, and what is graphene? It's a 2D aromatic, means you may consider many benzene nucleus are at 1, 2, this are adjacent together and forms this actually a 2-dimensional network. So in this case, graphene, we know that such type of kind of molecule can act as a conjugate semiconductor. Why? Because when we say this benzene, we consider about the concept of HOMO and LUMO. So highest molecular orbital and lowest unoccupied molecular orbital. Okay, we think in this way and we say, okay, HOMO have some amount of electron, LUMO have some amount of electron. Now when there are many bonds, for example, you are increasing the number, so due to this the number of electron increases, and what happens, this orbital energy levels, this orbital further couples together and ultimately the overall gap between HOMO and LUMO decreases. So consequently, if you add one additional electron, the instability is less, or if you to the conduct means the LUMO here, you may consider if you add one additional electron on the LUMO, instability is not that much. If you take one from HOMO, instability is also not that much. But actually better to say, instead of, for example, this graphene thing, instead of saying it's HOMO LUMO, we should say this, actually this HOMO should be considered as valence band or VB and this LUMO should be considered as conduction band of CV. So I shall not discuss those things in details, we will discuss in some other video. So from this, what we have learned, what message we are giving, actually if you want to take electrons from somewhere, it means you are doing oxidation. Okay, you are doing oxidation. We know oxidation means withdraw or taking an electron. And what does it mean by reduction? Reduction means addition of electron. Okay, so oxidation means minus electron, reduction means addition of electron. Now question is, if a molecule have so much electron, they are conjugated like graphene or porphyrin, they can act as both oxidant as well as reducing agent depending on the other chemical present in the reaction medium. For example, if you keep this porphyrin, for example, you know that this means porphyrin iron complex, they can undergo, when this iron oxidizes, porphyrin helps to stabilize the electron deficiency iron, means that when electron is required in the surroundings, this conjugated system can give its electron to the surrounding and stabilize, or when excess electron is there in the medium, so they can take, one of the example is potassium graphite. Okay, potassium graphite, I guess you know, it's a very famous reducing agent. Okay, potassium graphite. So those are the things, that's a real proof that a single molecule or particular kind of molecule can act as a oxidizing agent as well as reducing agent. Generally for small molecules, small organic molecules more specifically, if we say, they have a particular property, either they are electron rich means they are reducing, or they are electron deficient means oxidizing. But because of these unique property, that is conjugation and this HOMO-LUMO gap less, so they can act as both. So this is the unique lesson we have learned from today's lecture. Okay, so in conclusion, what we have learned today, this aromaticity is a huge stabilization energy and compound prefers to sacrifice this in a minimum extent, because the tendency of molecule is to remain stabilized. Why they will expense their reason to be stable, that is aromaticity. Okay, among all aromatic compound, benzene is maximum stable, and for that purpose you need to calculate per nuclear basis. And this, as I told, polynuclear aromatic compound can act as both acid and both accident and reducing agent as their electron reservoir. And another thing we just have explained, that is increase in conjugation result in decreasing HOMO-LUMO gap, better to say valence band, conduction band gap, and actually they became semiconductor, and in some cases they can become as a conductor. For example, graphene, they can act as a conductor, but smaller than graphene they can act as a semiconductor molecule also. Okay, so let's come to our questions answer. What is the product of this reaction? Actually, this is actually oxidation, KMnO4. So hint I have given, side chain oxidation of benzene. We know what produces side chain oxidation of toluene. If we say what it produces benzoic acid. We know under this condition. So similar thing will occur. Now question is which nucleus? This benzene nucleus means 1 or this pyridine nucleus 2 will undergo oxidation. Oxidation means taking of electron. So in which place the electron will be taken? The place which is more electron rich, from there electron will be taken and the reaction will occur. If you compare this actually this is quinoline nucleus, one part is pyridine, this number 2 part is pyridine and the other part is benzene. So because of the presence of this relatively more electronegative nitrogen, these two nucleus or pyridine nucleus is electron deficient, so it is difficult to take electron from pyridine nucleus and oxidize itself. So pyridine will remain unchanged. So consequently what will happen? There are actually two bonds. So here one bond and here one bond. We know side chain oxidation always result in carboxylic acid formation. There is one methyl, that's why carboxylic acid. If I take another methyl here, what will be the product? Then it will be dicarboxylic acid. So similar thing will happen. So what it will produce? It will produce this pyridine and 2 carboxylic acid. So similar thing, I guess student, you have observed oxidation during the oxidation of naphthalene. What that produces? Naphthalene produces phthalic acid. Some you can say that, sir, I have seen phthalic anhydride is produces after the oxidation. Remember student, the reactions are carried out in aqueous media. In aqueous medium anhydride doesn't form. What happened if you separate this phthalic acid or for example this pyridine dicarboxylic acid, then you heat, then you can expect anhydride formation. In aqueous medium anhydride doesn't occur. So answer of our question is option C, this one. Okay, so this is the overall discussion. Thanks for watching.